Welcome back, students, for this third lecture of this module where we are deriving the velocity potential of the ocean surface waves. Last time we concluded with this particular slide indicating the definition sketch of the wave motion, where we have told you what the water depth is. This figure is actually very important for understanding how this linear wave is represented. The wavelength is given as L at the top, the depth is indicated, wave height h is also given, seabed is shown. So, we from this point onward we will continue with our derivation. Now, we are going see we have listed the boundary conditions. One was w is equal to 0 at the bottom, second was we specified free surface, dynamic free surface boundary condition at the top, and now we start with the solution of the Laplace equation. So, Laplace equation in terms of velocity potential in 2 dimension, as we have assumed x and z, is del square phi by del x square is plus del square phi by del z square is equal to 0. To obtain the solution, a very simple method of separable is used to obtain the solution to this equation, which is 2.6. All right. Now, let us assume method of separable, phi of x z t can be written as x bar as a function of x, it can be separated, z bar as z, t bar as t. Now, if we substitute 2.7 this equation in 2.6, all right, because due to the velocity potential Laplace equation properties, we are able to separate x, z and t, okay, using the method of separable. What do we get? We get x double prime bar z bar t bar plus x bar z double prime whole bar and t bar is equal to 0. Here each prime denotes the differentiation once with respect to the particular independent variable. So, double means double differential. Now, if we divide both side by x bar, z bar and t bar, we get x bar x double prime bar by x bar is equal to minus of z double prime whole bar by z bar. This is the equation that we get. All right. Now, see, this is, let us say this is a constant minus k square, okay. Then we can write one of the equations from this will come x double prime bar plus k square x bar is equal to 0, and the second one will be z double prime bar minus k square z bar is equal to 0. These two are very famous equation. The solution for this is standard. So, x bar from 2.8 can be written as a cos kx plus b sin kx, all right. Whereas, z from equation number 2.9, solution to this type of equation is here. Solution to equations of type 2.9 is this one from equation 2.9, all right. We get x bar and z bar. So, we can simply write, so you see we had the solution that we initially assumed was phi x z t is x bar, z bar and t bar. So, we can write, instead of x bar we can write this one, instead of z bar we can write this one, and t bar remains as t bar, all right. Now, the solutions to phi are simple harmonic in time, that is because we know from previous that they are waves and periodic in time. Therefore, t bar can be simply replaced as cos t or sigma t, anything it can be replaced, and therefore, with each of the values of sin t or sigma t, we have 4 forms of phi. One will be one will be a cos kx multiplied by sin, the other would be a cos kx multiplied by cos, the other would be b sin kx multiplied by sine, and the fourth one would be b sin kx multiplied by sine. Okay. So, we can write 4 different terms. A1 we did not touch this this. So, a cos kx plus b sin kx multiplied by either sin sigma t or cos sigma t. Okay, there are going to be 2 terms when we assume t as a function of sin as sin sigma t, and there after multiplication with this, and there will be 2 other terms if instead of sin we assume cos s t bar t. So, total we can write 4 terms. Phi 1 will be a1 into c e to the power k z cos kx cos sigma t. Another thing would be a2 c e to the power k z plus d e to the power minus k sin kx sin sigma t. The third would be sin kx cos sigma t, and fourth would be cos kx sin sigma t. However, the total velocity potential is going to be sum of 2 of those, right? 2 of those. Which one we will come to it later, but for now we have assumed 4 different terms: phi 1, phi 2, phi 3, phi 4. One would be phi 1 minus phi 2, the other could be phi 3 minus phi 4, but that we will come to later. So, we have to see these terms phi 1, phi 2, phi 3, phi 4 have constants a 1, c, d, all right. Sigma is related to the time period, k is related to the wave period, that will come to it later, but more importantly we have to find these constants a 1, c and d. So, how to determine these constants? The constants are determined using the dynamic free surface boundary condition and the kinematic bottom boundary condition, as you would remember, because by the definition of the boundary condition we said that there could be infinite number of solutions to a governing equation. However, with the application of boundary condition we can find one or more unique solutions to the problem. That is what we are going to do. These constant will be determined from the boundary conditions. Let us consider phi 2. Phi 2 is one velocity potential that we have written here, okay, this one. So, what does it say? Phi 2 is a2 into c e to the power k z plus d e to the power minus k z into sin kx into sin sigma t. We call this equation number 2.10. If we apply the kinematic bottom boundary condition, which means if phi is the velocity potential, w is given by del phi del z, and that will be 0 at z is equal to minus d. If you apply that del phi del z at z is equal to minus d, it will be a2 into c e to the power minus k d minus d k e to the power k d into sin kx sin sigma t is equal to 0, right, at z is equal to minus d. So, now there is no z, but instead of z we have substituted d. So, a2 is not equal to 0, otherwise there is not going to be any wave. Also sin kx sin sigma t will not be 0, because there will be a velocity potential. If we substitute them to be either one of them to be 0, the velocity potential will become 0. So, that means these 3 terms cannot be 0. Therefore, the only thing is that this be 0, and if we utilize this we are going to get c as d into e to the power k d. So, with one boundary condition we have reduced our unknown by one number, okay. C is equal to, we have related c and d now. Now, if we substitute for c in equation 2.1 sorry 2.10, so instead of c we put 2d into what the term that we have got, we are going to get phi 2 is equal to 2a2 d into e to the power k d, okay, into sin kx sin sigma t, or simply we can write this is nothing but cos h k d plus z. All right, simple trigonometry. So, we have got phi 2 is 2a2 d e to the power k d cos h k d plus z. So, we are left with a2 and d for now. And if we do del phi del t at z is equal to 0, we get 2a2 d sigma e to the power k d cos h k d sin k x cos sigma t. And on assuming, if we assume that free surface elevation is a sin k x into cos sigma t, right. So, what we are going to do, here a is the wave amplitude, that is h by 2, this is our assumption, and by applying the free surface boundary condition, that eta is equal to 1 by g del phi 2 del t at z is equal to 0. So, first we have applied the bottom boundary condition. On the second step, we want to apply the dynamic free surface boundary condition. So, for applying the dynamic free surface boundary condition, we need to calculate this term 1 by g del phi 2 del t at z is equal to 0. All right, and this is what we get, this term, and this we equate to eta. Eta is the free surface, which is equal to a sin k x into cos sigma t. All right. So, simply what we do, eta is equal to, this is, sorry, all right. And after solving for this, we get 2a2 d e to the power k d as ag by sigma into 1 by cos h k d. And if we substitute these values into our original phi 2, we are going to get it as phi 2 is equal to ag by sigma cos h k d plus z cos h k d into sin k x into sin sigma t. All right. So, we have now, first what we did, we solved for Laplace equation, applied the two boundary conditions and obtained the value of the velocity potential phi 2, which is of the form ag by sigma into cos h k d plus z into cos h k d sin k x into sin sigma t. So, sigma is 2 pi by t and k is 2 pi by L. This is wavelength and this is time period. For you, the derivation is not important, but the results are. But the derivation is important in a way that it makes you appreciate how, starting from the basics, we can derive these wave equations, the velocity potential. I do not expect you to remember the derivation, but the steps you must know. Things like the specifying a governing equation. What are the governing equations? Governing equation is Laplace equation. For the boundary conditions, we utilize the Bernoulli's equation and the continuity equation, for example. So, we have obtained phi 2 here. All right. So, if we consider phi 3 and apply the same concepts, that phi 3 is equal to, we apply the kinematic boundary condition, this will give C is equal to d into e to the power k d. All right. And same procedure is repeated for the dynamic free surface boundary condition, and we get for phi 3 a term like this. You understand? Same procedure. So, phi 3 we get minus ag by sigma cos h k d plus z. Similarly, we get phi 3, and same procedure we do for phi 4 for obtaining the values, and what we get is phi 4 is Ag by sigma, a similar result we get. And we repeat the same procedure again for phi 1, applying the kinematic bottom boundary condition first and then applying the dynamic. See, I am skipping because it is essentially the same process. More important, so more important is this term. So, phi 1 we get is minus Ag by sigma cos hk d plus z. If you remember, phi 2 and phi 2 and phi 4 was positive with a positive sign, phi 4 and phi 1 was with the negative sign after the derivation. Now, you remember I said that the total velocity potential will be the summation of the two terms, right. So, our velocity potential is going to be phi 2 minus phi 1, or also in terms of phi 3 and phi 4 also. So, this becomes, so if you add two velocity potential, this was phi 2 and this one was with this one with a negative sign was phi 1. So, we get this. So, cos kx cos sigma t plus sin kx sin sigma t can be written as cos kx minus sigma t using trigonometry. All right. So, the final velocity potential, which the value, I mean the formula for which you are supposed to remember is this one, Ag by sigma cos hk into d plus z divided by cos hkd into cos kx minus sigma t. This is the final velocity potential. So, now if you see, we have determined phi a is the amplitude of the wave, right, sigma is the 2 pi by t, k is 2 pi by l, right. So, everything you know. So, as a function of x and t, we have found out the velocity potential here. As I said, this is the expression for the velocity potential for a propagating wave in a constant water depth. All right. So, this is at one particular constant water depth. This is the velocity potential which we have derived pure from hydraulic assumptions and conditions. Okay. Now, because we have got the velocity potential, we can finally write the term for eta. All right. We are going to check. So, eta can be written as, so 1 by g Ag by sigma. So, del phi del t at z is equal to 0 will come out to be this one. Okay. So, Ag can be written as, so if you, this g and g will cancel, right, sigma and sigma will cancel. All right. So, at z is equal to 0, this will also get cancelled. So, simply we will left with n is equal to a sin kx minus sigma t. All right. So, now this eta is periodic in x and t. If we locate a point and traverse along the wave such that at all time t our position relative to the waveform remains fixed. So, basically this term kx minus sigma from your earlier mechanics class, you would know this is what, this is the phase, right, kx minus sigma t. So, with this phase we do an experiment. What we do is, if we locate a point and traverse along the wave such that at any time t our position relative to the waveform remains fixed, okay, then this means that kx minus sigma t will be 0. Okay, phase difference is going to be 0, which means that kx minus sigma t is going to be constant. All right, because if phase will be constant, phase difference is going to be 0, and the speed with which we must move to accomplish this will be given by kx minus sigma t is equal to constant, or kx is equal to sigma t plus constant, right. And on differentiating, we can get this equation, we differentiate, we get k dx dt is equal to, we differentiate with respect to time, is equal to sigma, or dx by dt can be written as sigma by k, and sigma was nothing but 2 pi by t and k was nothing by 2 pi by l. So, it's become L by t, and that is the c, and c is the wave celerity. So, to determine the velocity of the wave, this is the, so this is how the wave celerity, that is length, wavelength by time period is the celerity, and this is the basis of finding the wave celerity, that if we locate a point and traverse along the wave such that at all time t our position relative to the waveform remains fixed. When this will happen? When we are going to move with the speed of the wave, and that our speed and wave speed c will be the same in that case, and that is what we have found out, that c is equal to L by t is the celerity of the wave with which we must be moving. All right. Now, if there is a wave that is moving in x direction, then we can simply write the velocity potential phi minus is equal to phi 2 plus phi 1, not minus phi 1, and then we will get nothing but with minus sign, minus Ag by sigma cos h kx sigma kx plus sigma t into cos h kd. So, what you do is you do x is equal to, so instead of kx plus sigma minus sigma t, it becomes cos kx plus sigma t. So, this is a different waveform. All right. So, in this case, since eta is 1 by g, we will also get a similar, it was remember it was kx minus sigma t, it becomes kx plus sigma t. So, the phase is changing when the wave is traveling in the negative direction. All right. Now, to obtain the celerity of the wave, in this case we have kx plus sigma t is equal to constant, same procedure is repeated. So, it will become minus c. All right. So, wave negative means negative celerity in the negative x direction. Now, one important thing after this derivation of the velocity potential is something called a dispersion relationship. That is one of the core concept of the wave mechanics. So, the relationship between wavelength, wave period and water depth is obtained as given below, okay, for the dispersion relationship. The main assumption while establishing the relationship is that since we are dealing with small amplitude waves, meaning that the slope of wave profile are so small that del eta by d eta by dt can be approximately said equal to the vertical component of the velocity w. All right. So, w can be written as d eta dt, or in differential form del eta del t plus c. W is what? Del eta by del t, because that is the vertical velocity, correct, d eta dt. So, that if you apply the total differentiation by total differentiation, it will be del eta del t plus del eta del x into del x del t. All right. So, wave slope being small means del eta by del x is equal to 0, which implies d eta by dt is equal to del eta by del t. All right. W is equal to del eta del t, but del W is also equal to minus del phi del z in form of velocity potential, correct. Hence, del eta by del t equal to minus del phi del z. We know the velocity potential, we know the equation of eta. Okay. If we do the differentiation of eta, what we get, del eta del t is equal to 1. So, if we do the if we differentiating the expression of eta, okay, what do we get? Del eta del t is equal to 1 by g, you remember that term at z is equal to 0, 1 by g del square phi by del t square. All right, eta was 1 by g del phi del t at z is equal to 0. So, if you differentiate this, you get del eta del t is equal to 1 by g del square phi by del t square at z is equal to 0. This is what it is written here. All right. So, we substitute del eta by del t, we get from here, all right. Where A is equal to, we write capital A is, where A here is h by 2 into g by sigma divided by 1 by cos h k d, and W is also minus del phi del z, that is minus a k sin h k d into cos k x sigma t, and we equate this, we will equate both these term a square sigma from the previous equation with this one here from the previous page, because both are same, correct, and on cancelling the common terms, what we get is sigma square by g is equal to k sin h k d divided by cos h k d, and this is nothing but tan h k d. Okay. So, sigma square can be written as g k into tan h k d. All right. Here sigma is the wave angular frequency equal to 2 by t, and k is equal to wave number, which is equal to 2 pi by l, as we have seen before. And this above equation can be written as 2 pi by t whole square is equal to g into 2 pi by l tan h k d. So, actually this is the famous dispersion relationship. Okay. So, but if substituting sigma and k in terms of t and l, we get L by t whole square is equal to g L by 2 pi into tan h k d, or c square is equal to, because L by t can be written as c square is equal to g by k tan h k d. So, the speed at which a wave moves in the direction of propagation as a function of water depth can be given by equation. Earlier we obtained the velocity potential at constant depth, but now we have found out the speed of the wave as a function of water depth. Since c is equal to L by t, we get c is equal to, see we are just writing it in a different form. So, c can be written as g L by 2 pi tan h k d, all right, or L is equal to g t square by 2 pi tan h k d. Since the unknown L occurs on both sides of equation 2.32, it has to be solved by trial and error, because k is nothing but 2 pi by L, all right. So, if you you want to, so this is the equation, dispersion, famous dispersion equation, sigma square is equal to j k tan h k d, which you must remember. All right, and doing some manipulation here and there, we can also write L is equal to tan h, L is equal to g t square by 2 pi tan h k d. Okay. And this is also a different form of dispersion relationship, and because this L appears on both sides of this equation 2.32, this equation, if needs to be solved, will be solved by trial and error method. Okay. So, I will stop at this point in this lecture, and when we start the next lecture, we are going to study the celerity in different water depth conditions. So, thank you so much for listening in this lecture, and I will see you in the next class.